Assalamualaikum warahmatullahi wabarakatuh and hi everyone. Okay, welcome back. After you have a short break for 1 week. So I'm going to finish my part for this subject, PTT 156. So let's begin. Okay. We're still in chemical material balance with reaction, but there is another part, new knowledge that you need to learn. Okay, before this, you learn the example that I gave to you is straightforward chemical reaction, which is use this symbol, right? So if this appear in your question, that means the reaction proceeds in single direction from your left to your right hand side, which is irreversible, where your reactant will be react together to produce your product. And at the end of your reaction, your limiting reactant will become zero eventually, right? But when there is some reaction where it can go reversible, meaning from right hand side to left hand side, and at the same time the left hand side can also change or react to produce your reactant again. Okay, the symbol that used for reversible reaction is this. Okay, if in your question shows this kind of symbol, that means the reaction is reversible. Okay, it can go forward and backward. However, this type of reaction will reach a equilibrium point when the rates of reaction for forward, meaning forward in this way and reverse in this way, is the same or equal. So that's mean at that time you have achieved the equilibrium point where the rate to the forward and reverse are the same. Okay. Basically in this in this PTT 156, you only need to know what is the meaning of the reversible equation, reversible reaction, what is the meaning behind it, and I will avoid to ask you in the exam question how to determine the molar flow rate or flow rate or mass flow rate by using this kind of question. But then you need to know lah. Okay. So basically, our aim is only to find equilibrium composition when the equilibrium point is achieved. Basically, when you have this kind of question, you are given the we call it as a constant, equilibrium constant. Okay, we see on the next example, which is example 1. So in this question, the water gas shift reaction where carbon monoxide react with water will produce carbon dioxide and also hydrogen. This is a reversible reaction which goes forward and reverse. Okay, and then proceed to equilibrium at a temperature Kelvin. The mole fraction of the reactive species certify the relation. So this one is given in your question, where KT is the reaction equilibrium constant and then give you the value where at temperature 1105 Kelvin, the equilibrium constant is equal to 1. Suppose the feed to a reactor contains 1 mole of CO or carbon monoxide, 2 mole of hydrogen oxide, 2 mole of water, and there is 9 carbon dioxide and also hydrogen. The reaction mixture comes to equilibrium at 1105 Kelvin, and what the question asks is equilibrium composition and the fractional conversion of the limiting reactant. Okay, how we are going to solve this? All right. First thing first, because it's asking for you to calculate the equilibrium composition, okay, and the limiting reactant. And this is the equation or relation that gave it to you, and y is the molar composition. Alright. Okay. Develop the extent of reaction. Basically, we use extent of reaction in order for us to calculate the amount of final composition for each item or for each chemicals. Okay. We know that okay, this one actually not for NCO. Sorry. This one, there is in the question stated that there is no carbon dioxide and hydrogen. So this one should be eliminate lah. So N total should be mole of carbon dioxide, carbon monoxide plus moles of water, which is equal to 3 mole. Okay. So I think you can develop your own extent of reaction for this chemical reaction. Why I use E here? Because it stands for equilibrium reaction. Okay, so that's why I put E. Okay, and then 1 mole is this one. Revise back the previous lecture where you want to find your extent of reaction. The equation become N final equal to N initial minus V theta. Okay, so minus or plus lah. If minus meaning is reactant, plus is it means that is a product. Okay, so since it stated that for carbon monoxide we have 1 mole for initial, so I straightly put here 1 mole minus 1 because your coefficient is 1. Same goes to final moles of water, where you have 2 mole at the initial, was stated in the question, minus extent of reaction in equilibrium. It's also minus because it's a reactant, and it is 1 in front of the extent of reaction. Okay, so since it's stated there's no non-carbon dioxide and also hydrogen, so I just straightforward put there lah. Okay, next. Sorry. So, this is molar composition, right? Because it's gave here because we are going to use this kind of relation. So, YCO means the molar composition of CO. So, what is the formula to find the molar composition of CO is NCO divided by total mole. Total mole we have 3 more here. And then you know that to find NCO, we have this 1 minus equilibrium constant divided by 3 mole. Okay. Next is H2O. Molar composition of H2O. How to find the molar composition of H2O? Where we use molar of H2O divided by 3, which is total mole of the system. So you know that NH2O is 2 minus the E divided by 3. Next is Next is YCO2. We have here NCO2 divided by 3. So you have NCO equal to SN of reaction divided by 3. And same goes for molar composition of hydrogen, where the equation should have mole of hydrogen divided total mole, which is 3, and this become like this. Okay, so for all four equation, you can plug in into the relation that gave it to you, and it become like this. Divided by YCO H2O, okay, equal to, since it said that the K equal to 1 at temperature of 1105, so you just straight away put 1 lah. Okay, so when you rearrange the equation, so this part, it needs your mathematics knowledge lah. So try to rearrange to get the value of delta E, and at the final you will get the extent of reaction of in equilibrium will be 0.667. Okay, so how to calculate so you need to calculate the equilibrium's composition. So you can directly, when you know the extent of reaction, then you can just plug in into your equation here, 1, 2, 3, 4. So you can directly get the answer for equilibrium composition. And then for the limiting reactant, 1 mole of CO plus 2 mole of H2O, and we know that we need 1 mole of CO to react with 1 mole of H2O based on this reaction. But since in your in the feed you have 1 mole of CO and 2 mole of H2O. So if we use 2 mole of H2O as a basis to find the limiting reactant, okay, times this one, you can use the ratio based on your chemical equation. So this one, 1 mole of CO, 1 mole of H2O. Where I get 1? Because I use this equation. So you can cancel it out. So when you have 2 mole H2O, you need 2 mole of CO in order for you to have a complete reaction. But in real situation, you only have 1 mole of CO. So the limiting reactant is CO. Okay, right. Next. So there is another 2 equation, 2 formula that you need to know, which is yield and selectivity. What is yield? Yield is moles of desired product form, which is in actual life, divided by moles that have been formed if should be formed, there is no side reaction, and limiting reactant has reacted completely. Okay. And the second one is selectivity. Moles of desired product divided by moles of undesired product. So this is where we learn about when you have 2 reactions that occurs simultaneously in one process. Okay. So this one is your equation how to find extent of reaction for multiple reaction. For a few reaction that occurred at the same time in your process. Okay, you see here. Consider the pair of reaction in which ethylene is oxidized either to ethylene oxide, which is your desired, or to carbon dioxide and water. And this one is your undesired product. So it's asking about the extent of reaction. Okay, so in this equation, we have two reaction that occur even though we use the same reactant. Okay, where ethylene is converted either into ethylene oxide or carbon dioxide. So in this question, I have labeled it up. For the desired one, we call it as equation 1, and the undesired reaction, I label it as second lah. Okay, so how we are going to develop the extent of reaction? We call back that formula to develop the equation is alright. So if we're talking about C2H4 and final and or moles of C2H4 final minus and C2H4 initial, so I put dot or 0. Okay, C minus, since it's a product, this is 1, the coefficient is 1, same goes the coefficient of the second reaction also 1. So minus theta 1 minus the extent of reaction 2. 1 means for reaction 1, 2 means for extent of reaction 2. Every reaction have their own extent of reaction. Okay, so we try for O2, oxygen. So moles of oxygen final be equal to moles of oxygen initial minus half, since the coefficient is half, extent of reaction 1 minus another 3 extent of reaction 2. Okay, why half? Because the coefficient is half for the first reaction. Why 3? Because the extent of the coefficient is 3 for the second reaction, Y minus because both are, because oxygen is the reactant. Okay, we see for the ethylene oxide, C2H40, the final moles of C2H50, final equal to, and C2H40 initial plus 1 lah, 1 theta external reaction 1. Y plus because it's a product, Y at in front is 1 because your coefficient is 1 from your chemical reaction for the first. Okay, so we try again for CO2, carbon dioxide. So final moles of CO2 equal moles of CO2 at the beginning plus, since it's a product, since it's a product, is plus how much? Look back at the coefficient, plus 2 percent of reaction 2. Okay, since there is no CO2 will be developed or will be produced on the first reaction, so we only focus on the second reaction. So same goes for hydrogen, same goes for the water. most of water for the final equal to moles of water at the beginning plus Y plus because the H2O is a product, plus how many? Plus 2 because the coefficient is 2, so the extend reaction 2 because it's a second reaction. So these are your extent of reaction equation. Okay, so we take another example, example 3. We have two also reaction, two simultaneously reaction, but okay, this is the first one and this one is second one. It's a non-reversible. Okay, it's straightforward. Both reactions take place in continuous reactor at a steady state. The feed contain 85 mole% of ethane and the balance is inert. The fractional conversion of ethane is 0.501 and the fractional yield of ethylene is 0.471. Calculate the molar composition of the product gas and the selectivity of ethylene to methane production. Okay, so first thing first, you need to develop the flow, the flow diagram. Okay. So what is inside input to the process? We have 85% of ethane, 0.85 C2, H6, and the rest is inert. So I put inert as I. How much? 0.15. And your product will come out as C2H4. We have C2H4, we have H2, we have CH4. We also have inert because it's not inert is something that not reacting with your product or your reactant. And since it said that the conversion of ethane is 0.501, means not all the product will be converted. So all cost we have C2H6 here. Okay. So give it level 1, 2, 3, 4, 5. Okay. So this is how your flow diagram looks like. But we're missing a few things here. Okay. Your basis. Okay. Basis is something like the total mole of output or total mole of any input stream. Okay. Since it's not stated here, you may assume your basis or your input. So let's see your so let's see. Gosh.